Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book Retrolinear. The subject of this lecture is matrix linear transformations, when we think of matrices as linear transformation, and in particular, their image and kernel. Let me remind you what a linear transformation is. So a linear transformation is when we have two vector spaces, V and W, and we have a function t from V to W. Then this t, if it's a function, could be a linear transformation or not. It will be a linear transformation if it has the following property. A linear transformation is a function, so it takes an element x in V and sends it to its corresponding element over there at t of x. And it sends y to its corresponding element t of y over in W. W is the codomain, V is the domain. But because V is a vector space, you can find x plus y. And the question is that, does x plus y have a choice in where it ends up? And if it's a linear transformation, it doesn't. It will have to end up at t of x plus t of y. Now, x plus y automatically goes to t of x plus y. So t of x plus y needs to be the same as t of x plus t of y, regardless of which vectors x and y in V you pick. That's one property of linear transformations. And the corresponding property for scalar multiplication is that t of alpha x should be the same as alpha t of x. So we say that t has to preserve addition and preserve scalar multiplication. This is what a linear transformation is. Now, one source of linear transformations are matrices, and this is something we have seen before, but in this lecture, I'm trying to bring together all the different things we know about matrix transformations. And I'm going to state that in the form of a lemma, because I'm claiming that I have a way of creating linear transformations from matrices. So you have a matrix A, m by n, a matrix with real entries, and that defines for you a map from Rn to Rm, which I'm going to call L sub A. You could call it A if you want also, but just to distinguish the map from the matrix, I'm going to call the map, the function, L sub A. But to tell you what a function is, I have to tell you the domain and codomain, which I already did, Rn and Rm, but I also have to tell you the rule, the formula, the way that LA takes elements of Rn and gives you elements of Rm, and that's given by matrix multiplication. So LA of x is A times x. So x is something in Rn, x is not a number, it's a column vector with n entries, and how do you send it over? You take the matrix A and multiply it by it. A is m by n, x is n by 1, and when you multiply those, you get an m by 1 column vector, which is an element of Rm. Then this lemma tells us that this is always a linear transformation. Regardless of the matrix or its size, you will always get such a linear transformation. And we have seen the proof in a previous video, but I will go over it quickly. But before doing that, let me give you an example. So, for example, this A is a 3 by 2 matrix. Because it's a 3 by 2 matrix, it gives us a map from R2 to R3. And how does it do that? So, for example, if you want to say what LA of alpha beta is an element of R2. Where does it go? Well, you multiply it by A. A times alpha beta is where it goes. And when you do that, that means you take the matrix and multiply it by alpha beta. And if you do that, you get 3 alpha minus 2 beta minus beta and alpha plus 2 beta. So that element alpha beta of R2 ended up in this element 3 alpha minus 2 beta minus beta alpha plus 2 beta, which is an element of R3. So you have a function from R2 to R3, and the lemma claims that this is always a linear transformation, and I'm going to give you a quick proof for that. So I have to show you that it preserves addition and scalar multiplication. So A is an m by n, LA defined from Rn to Rm by LAX is AX. So you, again, same thing as we had before. Why is this a linear transformation? And the answer is that, well, pick two elements in Rn and a scalar alpha, and let's see if it is or not. So what's LA of x plus y? I want it to be LA of x plus LA of y, because I'm trying to show that this is a linear transformation. But a priori, I don't know that. I have to prove that. Now, by definition, LA of x is AX. LA of apple is A times apple. LA of x plus y is A times x plus y. And A times x plus y are two column vectors. And when you multiply a matrix by column vector, you can distribute and you get AX plus AY. Now, AX is LA of x, and y is LA of y. So I proved that LA of x plus y is LA of x plus LA of y, which preserves addition. And I can do the same thing with scalar multiplication. LA of alpha x is a times alpha x. Alpha is just a constant. It doesn't matter if you multiply it first by x or wait till the end and multiply it. And so this is alpha times a of x. And so that's alpha times LA of x. And that's exactly what I needed to show that matrix transformations, these functions that you make from matrices, are always a linear transformation. Now, before we go on, let me just say where we are at with terms of matrices. If an n by n matrix walks through the door, if you meet an n by n matrix, you can be polite and introduce yourself. But then you're going to think about, well, what should I be thinking of this new friend that I found, this matrix A? And at this point, we have 3 ways to think of it. So one way would be to say, well, I just got an array of numbers. If it's n by m, it has n rows and m columns. So it's n numbers arranged in a particular way, like a table. Maybe the rows mean something, the columns mean something, and this table is telling me something about those things. That's the usual way that you may have been thinking about matrices before linear algebra. Another way is one that we have been developing in our course in linear algebra, is that when you see a matrix, you think of the vector subspaces associated with that matrix. So you think of the column space, the row space, and the null space. The column space is the span of the columns, the row space is the span of the rows, and the null space are the solutions to AX equals 0. And then you can use the machinery of linear algebra to try to help you say something about the matrix using these vector spaces, these subspaces. But now we have a third way, and that's to think of the matrix as a linear transformation from Rm to Rn. Now, we have been talking about matrices over the reals, but for second-time readers and third-time viewers, you can have the matrix be over any field, meaning that the entries don't really have to be real numbers. They could come from any field. They could come from complex numbers. They could come from rational numbers. They could come from a finite field like ZP or Z mod PZ, the integers mod a prime, P, or any field, finite or infinite. And if you do that, you get a linear transformation from Fm to Fm, Fm to Fn. Fm is m tuples where the entries are from the field F. So again, if this is the first time through linear algebra, just ignore that the final comment. Okay, so here's an example. Let's say someone gives us a map from R2 to R2, and it sends alpha beta to 4 alpha plus 7, and then 7 alpha minus 4. That's what the map is. And you want to know if this is a linear transformation or not. We just showed that matrix in the linear transformations that come from matrices are linear transformations, but this one didn't automatically come from a matrix. So how would we show it's a linear transformation? We could do what we did for the matrix transformations and show that T of x plus y is T of x plus T of y, and T of alpha x is alpha T of x. Or now that we know matrix transformations are linear transformations, we could just note that if we make the matrix whose first row is 4, 7, and the second row is 7 minus 4, then T is the linear transformation LA, because from this matrix, we get that linear transformation from R2 to R2, since A is 2 by 2. And the rule for it is that LA of alpha beta is going to be 4 alpha plus 7 beta, 7 alpha minus 4 beta. If you just multiply the matrix by alpha beta, that's what you get. And that's exactly what T of alpha beta is. So LA is T, and because LA is a linear transformation, so is T. So this is a quick way of deciding if something is a linear transformation by realizing that there's a matrix in the background, even if they didn't give it to you at the beginning, that is really generating that linear transformation. Now, you might say, well, could this be a fool's errand? Like, could it be that I'm looking for that matrix and never find it? And the spoiler alert is that that will never happen. If you're going from a finite dimensional vector space to another, and you have a linear transformation, there will always be a matrix that will do the job for you. And that will be the subject of much later lectures when we look at that relationship a little bit more closely. Okay. Now we want to ask the major question in this video, which is that okay, you have your matrix, you have your linear transformation, but what can you say about its kernel and the image? That's what I want to address now. Before I do that, I want to remind you what the kernel and the image are. So you have a linear transformation from V to W. So V and W are vector spaces. They have zeros, for example. There's 0 of V and 0 of W. Linear transformations, by the way, always send 0 of the vector space V to the 0 of the vector space W. They don't have a choice in that. That follows from the properties of linear transformations. We have seen a proof of that. One way to, let's just leave it at that. Now, image of T, what is that? That's the elements in W that are hit by something, that are the images of some element from V. So when you take elements of V and they send them over, you might not get everything in W. W is the codomain. It's the target set. It's the canvas on which you're throwing elements of V, but you might not hit everything. An image is the stuff that you do hit. And in fact, the linear transformation T really doesn't see outside of the image, doesn't have to give you any information about what's not in the image. It only tells you things about the image. And the kernel of T is all the elements that go to the 0 of W. And among them is 0 of V, but there could be more. So the kernel is all the collection of elements in V that go to the 0 of W. And the image is elements in W that are hit by something. Among them is 0 of W because 0 of V hits it. Okay, I'm going to now repeat myself again with the same things, but say it a little bit more formally. So the setup is that we have two vector spaces. We have a linear transformation. So the kernel is all the things that go to 0, is all the V in V that go to 0, and it's called the kernel of T, or the null space of T. That's an alternate name for it. And one of the things we know about it that we talked about in the video on kernels is that kernel of T is not just a bunch of vectors in V that go to 0. They form a subspace. Because they form a subspace, they have a dimension. The dimension of that is called the nullity of T. And T is 1-to-1 if and only if the kernel is the 0 vector. So the kernel controls 1-to-1ness. And one part of that makes sense. If T is 1-to-1, of course, since 0 goes to 0, nothing else can go to 0 if T is 1-to-1. On the other hand, it's not clear why, if 0 is the only thing that goes to 0, if the kernel is just the 0 vector, why is it that two other elements can't go to the same place, but they can't? And we proved that. That's sort of a nifty little proof. Look at the video about the kernel for that. The image is defined in this way. It's all the W in W for which such that there exists, backwards Z means there exists some V in V with the property that T of V is W. So it means that you look for W's in W and you say, well, is this in the image or not? And you check, can I find a V in the domain such that if I apply the function to it, I get W? That's the image. Another alternative name for it is the range. And again, image is also a subspace, but this time a subspace of the codomain of W. And the dimension of the image is called the rank. But just like the one-to-one, we can switch asking about one-to-oneness, which asking about the kernel. We can switch asking about onto-ness with asking about image, except this doesn't really need a proof. This is just a definition. T's onto, meaning that everything is hit, if everything is hit, which means that the image is W. Okay, now let's go to matrix transformations. So A is an M by N matrix. We have our corresponding linear transformation. So we have a linear transformation from Rn to Rm that's defined by matrix multiplication. You take, where does X go? It goes to AX. And we want to know what the kernel of this map is. So let's think about what the kernel of the linear transformation, that's really a matrix transformation, what can we say about that? Well, what is the kernel of LA? That means that something is in the kernel if it goes to 0. That was the definition. So X is in the kernel of LA if LA of X is the 0 of W. But what is LA of X? Well, LA of X is AX. So saying LA of X is 0 is the same as saying that AX is 0. So AX is 0 is the same as saying LA of X goes to 0. The W here is Rm, of course. And so find something is in the kernel if and only if what? If A times X is 0. But what are those elements for which A times X is 0? That's exactly the null space of A. So X is in the kernel of LA if and only if X is in the null space of the matrix A. So we have found a connection between the matrix A and the linear transformation LA. And what we have found is that the kernel of LA is the null space of A. One reason we want to think of matrices as linear transformations is that it allows us to use the imagery, the vocabulary, the concepts of functions, of linear transformations, something that just right off the bat we might not be thinking about when we're looking at a matrix. So here's one example of that. Null space of a matrix is a concept that we know and familiar with from matrices. But kernel is something about linear transformations. And we have an imagery with that. It's some of the elements in the domain that got mapped to 0. And now we have translated that. The kernel of LA is the same as the null space of A. Okay, now let's switch to the image. So A is an M by N matrix again, same setup. LA is the linear transformation from Rn to Rm, and it's defined by LA of X is AX. And what can we say about the image of LA? Well, how do we find the image of a linear transformation? So we talked about this in detail in the video on image of a linear transformation. There's various ways of finding the image of a linear transformation, but one way is to realize that all you need to know about a linear transformation is to know where basis elements of the domain go. So you find a basis for the domain, you send them over, and they will give you a spanning set for the image. Why do they give you a spanning set? Well, they are in the image, so their linear combinations will continue to be in the image because the image is a subspace, but you can't get anything else because anything else in the image came from something, and that something is a linear combination of those basis elements. And if you write it as a linear combination of those basis elements and then apply the linear transformation, you see that you will get something that's a linear combination of the images of those basis elements. This again we talked about this. I wrote it down in the video on the image. So what we do is that we pick a basis for Rn. In this, I pick the standard basis E1 through En. Ei, the ith one among those, is the one that has 0 everywhere except for 1 in the ith coordinate and 0s everywhere else. And E1 has a 1 at the top and 0s everywhere else. And this is the standard basis. I'm going to send these guys over, and I won't get a basis for the image, but I will get a spanning set for the image. Possibly a basis, but doesn't have to be. So image of LA is the span of what? LA of E1, LA of E2, LA of En. So I take E1, E2 through En, apply LA to them, and then find their linear combinations, and that's what the image is. So let's see what this means. So what is LA of EI? Well, LA of anything is A times that. So you have to multiply A by that column vector. But how do you, so we're, LA of EI is A times EI. What's EI? EI is this column vector. It's the ith element in the standard basis for Rn. How do you multiply a matrix by a column vector? One way to do it is to say you get a linear combination of the columns with the scalars coming from the column vector. To multiply a matrix by a column vector, you get a linear combination of the columns with the scalars coming from the column vector. But this column vector EI has mostly zeros. Actually only has 1, 1. So when you use those scalars as the linear to make a linear combination of the columns, the only column that will get anything other than 0 is the ith column. And so when we find A times EI, actually what we get is just the ith column of A. So image of LA was the span of these kinds of things, but what are these? The first one is the first column of A, the second one, second column of A, and so forth. So what we've just found is that the image of LA is the span of the first column of A, second column of A, nth column of A, but that has a name. That's called the column space. And so the image of LA is exactly the column space of A. So we found that whenever you have a matrix and you make a linear transformation out of it, the image of that linear transformation is the same as the column space of the matrix. Okay, so the things that we just showed, I'm going to write it down as a theorem. So A is an n by n matrix. LA from Rn to Rm is the corresponding linear transformation, the same setup as we've had all along. And it's defined by LA of X is AX. Then, so what did we prove? We proved that the kernel of the linear transformation is the same as the null space of the matrix. The image of the linear transformation is the same as the column space of the matrix. And because of that, their dimensions of these are going to be equal as well. So the dimension of the kernel of LA is the nullity of A. That will be the same as nullity of A. and the rank of LA, which is the dimension of the image of LA, will be the rank of A. And actually, that's why we use the word rank and nullity for dimension of the kernel and the image of a linear transformation, because in this case, in the case of a matrix transformation, it actually corresponds to the nullity and rank of a matrix. So whenever you have a matrix, you think of it as a linear transformation. And as soon as you think of it as a linear transformation, you know that things about the matrix tells you things about the linear transformation and vice versa. Sometimes it might be helpful to think of a matrix as a linear transformation because you want to learn something about the matrix. Sometimes you have a linear transformation and you want to think of it as coming from a matrix because the matrix tells you something about the linear transformation. So the information goes both ways. Okay, I'm done with this lecture, but let me give you a preview of what comes next, the next episode in this series. So in the next video, we will be looking at the relationship between the rank and nullity of a linear transformation. So rank is the dimension of the image, nullity is the dimension of the kernel, and they live in different worlds. And so a priori, you might think, well, okay, they don't have anything to do with each other, but they do for vector spaces and for a linear transformation. And the relationship I'm going to be calling the dimension theorem, and it's a pretty important theorem, because matrix transformations are also linear transformations. This also gives us a relationship between the rank and nullity of a matrix. And that relationship is sometimes called the rank nullity theorem, but it's the same one. So we will be doing this one thing, which is called the dimension theorem or rank nullity theorem, depending on your point of view. But in either case, it's an important theorem that gives us a relationship between the kernel and the image, or the column space and the null space. Till next time.